Hi, we're pleased to be presenting our work called Dual Diffusion, Unifying Image Generation and Understanding with a Single Model. Here we propose a multimodal model that directly learns diffusion processes on both text and images capable of image generation, captioning, and visual question answering. This project was completed with collaborators across Carnegie Mellon University, the TikTok ByteDance Seed Foundation team, and Yale. So generally, multimodal models are capable of reasoning between two modalities. Here we focus on text and images. In one direction, we have text-to-image models, such as Stable Diffusion, DALL-E, ImageGen, and more. In the other direction, we have vision language models, such as Lava, MiniGPT-4, Blip2, and so on. A natural question arises: is it possible to build models capable of reasoning in both directions? So given an input text, the model would be capable of generating the corresponding image, and given an image, the model can generate the corresponding caption. Finally, given an image and question, our model can reason about the image and generate an answer. So when the underlying model is an LLM, this has been shown to be possible. However, there is a lot of redundancy in the current recipe for most generalist models. So basically, for vision language models, we have the first two modules here, and text-image models, we have the second two, and in a generalist model, we just have overlap across both. So our goal was to try to simplify this recipe. We wanted to just have two components, an image and a text module, that were deeply interconnected. This is also useful, for example, if you want to unlock the latent image understanding capabilities of an existing T2I model. So a natural way to do this without introducing any causal loops between causal components is to have diffusion on both branches. Curiously, diffusion-based generalist models actually don't really exist in the literature, and we'll talk about that. The only partial matches are versatile diffusion and unit diffuser, but they don't support the full suite of multimodal tasks. Using diffusion has certain advantages, especially in multimodal settings. First, the cost of sampling from the model is not fixed. Unlike autoregressive models, computation time is not tied to the length of the sequence you're sampling. Next, sampling can occur in any order. Autoregressive models sample left to right, and this is useful for text, but in multimodal settings, images and text can be interwoven, and in diffusion models, this ordering will not affect the model's ability to reason. Third, unlike autoregressive models, diffusion models can refine a token after it's sampled. And finally, there have been a lot of exciting recent advancements in diffusion modeling on text. So let's quickly review the two types of diffusion used in our method. Continuous diffusion is defined on continuous value data such as images or audio. The forward process involves gradually adding continuous Gaussian noise to the signal, and the model learns to reverse this process by predicting diffusion targets such as the noise or velocity field. Masked discrete diffusion is defined on discrete value data such as text or other categorical tokens. The forward process involves a categorical diffusion process with an absorbing state, which is the masked token. The model learns to reverse this process by directly predicting the unmasked sequence via a cross-entropy loss. Our diffusion transformer has a dual branch architecture that communicates via full cross-attention in each layer. On the text side, the model performs discrete masked diffusion on text tokens, so masked text and clean images are input to the model, and a loss is applied to the text branch outputs. On the image side, the model performs continuous diffusion on VAE latents. Here, clean text and noisy images are input to the model, and a loss is applied to the image branch outputs. Finally, diffusion time is only provided for image diffusion. So there are two types of text generation that we're specifically interested in. On the left, we have a figure demonstrating our pipeline. So there's always an image input, and then there are input tokens above and output tokens below. In image captioning, all tokens start as masked tokens and are denoised to produce the caption. In visual question answering, some tokens, the question tokens start unmasked and only the answer portion is denoised. To unlock text generation capabilities while maintaining compatibility, we make some strategic changes to the SD3 architecture. So first, we drop both clip text encoders since they have a very short context length. Second, we add a text head to the text embedding branch of the MMDIT model. And third, we unfreeze only the mask token embedding in the T5 model for a portion of training. We train our model in 3 stages. We use a combined text and image loss, and for stage 1, we start with a low resource pre-training step where we use a recaptioned version of datacomp and keep the text token length at only 64 tokens and resolution at only 256 by 256. Next, we fine-tune with higher quality images using a data mix consisting of shared GPT-4v pre-training data and a recaptioned OpenImages v4. Finally, we instruction fine-tune on several vision language datasets combining the Lava datasets, TextVQA, and VizWiz datasets. Finally, let's talk evaluation. We run our dual diffusion model against a large selection of VQA tasks as well as COCO captioning. One thing we observed was that specialized unidirectional LLMs still form a very strong baseline for text-based visual understanding. We think there's 2 main reasons for this. First, these models use the clip embedding, which is known to be a strong representation. We wanted specifically to explore the innate visual understanding capabilities of our T2I model. And second, these models benefit from fine-tuning existing LLMs while we train our text branch from scratch. Even so, we already find that we have competitive performance against other generalist multimodal models. Note that with the exception of Show-O, our model is at least 3 times smaller than other models highlighted in this table in terms of trainable parameters. Next, we compare specifically against related work on diffusion-only models. So, ruling out non-text diffusion models, none are capable of VQA, but of these, only Unidiffuser actually supports text generation in their public code, and only captioning, not question answering. So, we evaluate against Unidiffuser by taking generated captions and feeding it to a GPT-4 model. GPT-4 then answers the question given the caption. Compared to Unidiffuser, our model had significantly improved performance on this benchmark. On the image generation side, we found strong performance on the GenEval and T2I CompBench benchmarks. Interestingly, we also have improvement over SD3. This suggests that improving the image understanding of the model also has downstream effects on the image generation capabilities. This improvement extends past prompt following and also applies to general image quality. In particular, we compare using the COCO dataset, which contains everyday images with high object density, and the MJHQ30K dataset, which contains images of high aesthetic value, and we see improvements here. In conclusion, we introduced a novel diffusion-based multimodal model that is capable of text and image generation and understanding. We show that this potential can be unlocked from a T2I model by simply adding architecture tweaks and fine-tuning. And finally, we observed that the joint diffusion loss improves image generation performance both in terms of prompt following and image quality. Thank you.